so far we've been thinking about a set as a space of possibilities, right? A set gives us this collection of objects satisfying some membership condition, right? Which I guess creates this subset when compared to the universal set U. So if I have a set called A, well, basically this set, let's just do that X is an element of A, where we have this particular predicate associated to A, the set A, right? So, well, obviously we're thinking about the membership of the elements, of these individual elements, X's, as a unary predicate, P of X. And the object either satisfies the condition of P of X, right? So we would have an associated true or false cases, right? So if this arbitrary element actually inside the universal set satisfies the condition of P of X, whatever the P of X is, it's just this predicate, we would have to assign either true or false. So already there is a very important structure associated to what we're doing, right? Because this leads to distinction between what's inside and what's outside. So it creates, so we have this like universe, this everything. Imagine this is the universal set, and this, what we're creating with the predicates, it creates this space, this little boundary, right? Right? So instead of worrying about the entire space, we just break it down, break the space down into little parts, like this, right? Due to this property, again, this logical property predicates. Okay? So let's say now we have two different sets. So we have set A, I'm going to write it again, X, this arbitrary element, part of the universal set, and it satisfies this particular predicate, P of X. And I'm going to introduce another one. X is an element of U, where there's a different predicate this time. It's like Q of X, right? So what do we have here? What are we saying? Well, structurally speaking, I'm seeing two different or independent spaces of possibility. So each of these subregions within the universe, A and B, they represent different or independent spaces of possibility. So that means that A gives me one collection of possible choices, and B gives me something else, something other than the collection of possible choices out in the A, right? So, and most importantly here, nothing yet tells that the element of A has something to do with the elements of B. So again, as I said, that makes them completely independent. But at this stage, I would like to ask, well, then what does it mean to make one choice from A and one choice from B simultaneously? If I were to make, again, some simultaneous choices from A first and then from B second, what's that gonna look like? How am I gonna translate it into like logical, mathematical language? Well, this is where we're gonna start talking about the Cartesian product, because the Cartesian product exactly does this. So the Cartesian product between two independent sets, A and B, which have nothing to do with one another, but like we're asking, hey, let's make one choice from the collection of elements from A, and let's make the other choice from B. And that's exactly what we're doing. So the way I denote the Cartesian product, it's pretty simple. It's just looks like that. The multiplication, it's like the multiplication of two sets, which is not what's going on. Multiplication is something else here. We're doing the Cartesian, we're taking the Cartesian product, right? So this, the Cartesian product, represents the space of all simultaneous choices. So this is the simultaneous choices, all the simultaneous choices out there. And the product, the arbitrary element within this space of simultaneous choice. This is a space, by the way. It's like the previous spaces, but this new space we created through Cartesian product, it's this, again, simultaneous, making simultaneous choices, and our elements. This is going to be just any element, you know. So this denotes to, well, A has to be an element of A, and obviously B is an element of B. And obviously we have the associated predicate still present, right? It was P of X for A, set A, and Q of X for B, right? I'll talk about the predicate part very soon here, right? Then we can ask, the natural, I guess, connection we can make from here is how is taking the Cartesian product is different from union, because we've talked about union before, right? Union is just an operator, a set operator, right? So I'll give you an example of a union very quickly and do an interpretation of the structure of it, right? So if I were to take the union between these two sets, we're talking about the same sets, by the way. So A and B, basically what this communicates is that I choose an object that comes from A or from B, because in logical language, you translate union to be an or statement. It is an or statement all the time, not an and would correspond to the intersection, right? So that's what we're doing, right? So choose an object that comes from A or from B, which in turn creates, I guess, cases, right? So this arbitrary element we choose could either be just part of A or just part of B or all combined. So it could be X as an element of A and B. This literally what this means. I'm just breaking it down and just, I guess, giving the membership conditions, possible membership conditions of this statement right here on top. Okay? But again, the Cartesian product is different. It's something else. Because this union merges possibilities into one common space, right? I'm not creating a new space using union or intersection. These are just again, just operators, set operators. Okay, so union merges possibilities into a common place. Merges, I guess, possibilities or choices. Possibilities into a common area. And, well, you know that the Cartesian product does something completely different, right? So the Cartesian product, what it does is that it preserves both choices at once. So in fact, okay, so we have two of these elements, sets, my bad. What we're going to do with the Cartesian product here is that we choose one thing from A and one thing from B. And neither coordinate is going to be disappearing. They're both going to be present at the same time, simultaneously, right? So instead of collapsing two spaces into one collection, we basically create this new kind of object, okay? And that object is, again, called the ordered pair. This is just a general